All right, in this section, we're going to be taking a look at the root test. And this is our final test that we're going to be constructing here in Chapter 5, as this is our last section in Chapter 5. Now, before we read through what the root test actually looks like, I think it'll be an important thing to recall that we've been, again, creating this kind of entire list of different strategies, different tests, and types of series. And a couple things that are important to note about this is, again, that the only time we've actually ever been able to find in exact, precise sum of a series has been with telescoping and geometric. Because here, we can find S sub n, and so we were able to find an exact sum. With an alternating series, we were able to estimate the sum, right? We were able to kind of bound it. But in everywhere else, we were only really able to say that if a series converged, we just knew it converged to something. Now, the root test really isn't any different, but it's important that you have this page kind of almost locked in your mind. This is kind of like our list of integral technique or integration techniques we had on the last exam. You need to, during an exam or as you're working on a problem, be able to kind of visualize this list. So whether right now you take a screenshot or a photo or you make your own page that summarizes this idea or the ideas here, I think that would be a really good thing to attempt to try to do. Okay, so we're going to take a look really quickly then at the root test here and try to get a sense of how it works, what it's good for. All right, so here's what the root test says. Consider the series starting when k goes from 1 to infinity, and let's have rho again be the answer to a limit. Notice that both these limits here are the exact same limit. One of them just has this kth root being expressed, and the other has rewritten that kth root as a power of 1 over k. So both these are the same, they're just written slightly differently. But again, we have some very similar conclusions to what we had last time with the ratio test. We have that if the result of this limit is less than 1, then the series converges absolutely, which of course we know means that it converges regularly. And if I get something greater than 1 or infinite, the series diverges. And unfortunately, again, if I get exactly 1, inconclusive is the result. I don't know what to make of that. So we're not going to go through the proof of this particular test here, but we will try to take a look quickly at example 1 to see how we can actually use it. So I want to determine here in example 1 with justification whether this series converges or diverges. Now, one of the big giveaways that might at least prompt me to think that the root test is a good call to use is the fact here that I'm going to be doing a kth root when I set up this limit. Notice that's not a choice, that's a demand. I have to choose a kth root. I can't do a square root, I can't do a cube root, I can't do anything except a kth root. So when I look at this series here and I recognize that there's something with a power of k, I recognize that if I did a kth root, those things might be able to cancel out. And therefore, that would allow me to maybe make this limit calculation become really easy really quickly. So that's at least the idea behind this. Now, of course, before I use the root test, I might want to go ahead and make sure that all the conditions. So really quickly, take a look at the theorem up there and try to consider for yourself, what are the conditions that I need in order to be able to use the root test? Okay, it's kind of awkward if you were looking at that box up there. There's nothing in this box that tells me anything about conditions because there are no conditions. As long as I have a series, I'm good to go. So I'm actually just going to go ahead and start by calculating this immediately. So let's see. I'm going to go ahead and state that we calculate rho is going to be calculated by doing a limit as k goes towards infinity. I'm going to be doing the kth root, notice, of the absolute value of that formula that was on the inside of the series. Okay, so this is what I'm going to attempt to compute. Now, this is kind of a little bit awkward because you'll notice again that the first thing I'm going to have to resolve are those absolute value bars. You have to do that first. It's a grouping symbol. You can't just bypass that. So fortunately, I can recognize here that, wait a minute, the smallest number that's going to get plugged in for that natural or into that natural log is a 1 or a k, which means the total inside is its smallest a 2. We already know that the natural log function is above 0. That is, it's a positive result as long as I plug in numbers bigger than 1. So as long as I get an input here total of bigger than 1, I know I get something positive. And very clearly, since we're going to start plugging in things like k is a 1, k is a 2, I'm going to get positive stuff here. So these absolute value bars in this actually have no effect. It's not that I'm just removing them because I don't want them there. It's that they actually legitimately have no impact whatsoever on the value of that fraction. Now, once I've gone ahead and I've written something like this, I can see that, wow, well, this is going to be really easy to simplify. I can do the kth root of the top of this fraction. The kth root of the top up here is just going to be 1. And the kth root in the denominator is going to be the natural log of k plus 1. So this becomes super easy. And then I can crunch out this limit really fast. That's the limit of 0. And I know 0 is less than 1. So by the root test, the given series converges. Boom, an argument just that short. So this is how this root test can actually get used and the way that we'll imagine using it. The hardest is going to be thinking through these absolute value bar removals or adjustments. And in the next video, we'll see kind of how that comes into play when we take a look at example 2.